Hello and welcome back to another video with It's Dr. Dan, and today we're going to be practicing stoichiometry together. And the whole entire idea here is we're going to be mapping out all of the different types of stoichiometry because over the past series of weeks I've been posting many different videos on gas law stoichiometry, solution stoichiometry, mass to mass stoichiometry, enthalpy stoichiometry. There are tons of different versions of how all this can be converted. Now, when we're kind of mapping it all out, the big thing is, well, what do they all have in common? What links them all together? And the big thing is what brings them all together is the mole, right? The goal in the end is always the mole, meaning how exactly do we convert to that point, right? Stoichiometry is taking the balanced chemical equation and essentially using it to define mole to mole ratios to be able to predict how much of a chemical compound we can make, how much do we need, maybe how much we can theoretically have. There are all kinds of important concepts that link all of these different factors together. And that's what we're going to be doing today is mapping them all out. Now, one thing is, like I said, this is all coming down to predicting and balancing. So it's taking all these skills together. So this is a little bit more of an advanced video. That's something that's more, are you ready for it after going through all these little tips and tricks, after learning about how to balance and go through chemical reactions. Now, the types of problems that you're going to be seeing could very much range depending on, well, what is it that your problem could be asking? You have to be able to solve limiting reactant problems, meaning you're starting with two different masses and you want to know what runs out first. You want to know maybe how much you will make in a chemical reaction. So, how much product do you have? How much do you need, which is how much reactant do you have? Maybe you need to calculate the mass or the volume or the molarity or moles or energy, or even going back to particles with Avogadro's number. There are many different concepts that you can calculate once you get to moles. And then finally, maybe you have to do percent yield to determine how good was your original number using molar maps. So let's take a look at it, trying to put the entire thing together to see what does a molar map look like and trying to convert from one thing to another. When I first came to understanding a mole map, the whole idea is where exactly you were starting, which was how much, when you start with grams, you could use molar mass by looking at your periodic table, defining the molar mass, and you could convert that to a number of moles. Now, from there, you had essentially the chemical equation that is balanced in the middle, and you can go from moles to moles using that chemical equation, searching this new chemical's molar mass again, and then convert it to grams. This is what was learned back in chapter 5. Now, from there, you went even beyond that and learned even more concepts, which all started with actually just looking at gas laws. Now, when it comes to gas stoichiometry, the whole idea here is you were using the ideal gas law to bridge this even farther, expanding this concept of moles, right? If you were given the volume of a gas or its pressure, or maybe even its temperature, you could use the ideal gas law to get to moles. You could also use STP as well, using molar volume to bridge that gap as well. There were multiple pathways. So gases got brought into the equation. Now, was that all there was as well? Well, we also had solutions too. So if we wanted to complete this picture, we also had the concept of molarity using solutions, right? Where we could essentially link together taking the volume or the concentration of a solution and convert that to moles too. There were all kinds of different moles and pathways to get to this middle step. So use this to really be able to try to help you map out your guideline because remember, even though your goal is the mole, which is right here in the middle, you always want to let your units guide your process to be able to see how exactly are they canceling so that way you can get from one step to the next when you're going through all these individual steps. Let's take a look at some of these some of these different problems that are going to be bridging between all these different pathways to be able to map out and get our final answer. So we're going to be kind of crossing borders here and mixing everything together. Let's take a look. An amount of nitrogen gas must be produced in an instant in airbags. So the first thing you always need to do is you need to balance the chemical equation, and sometimes you might even have to predict it depending on what's given to you. So this is always if it's needed. Now, if we look at this problem, we can see sodium nitride breaks down into sodium and nitrogen gas. And you can quickly see that it is not balanced, right? On the left-hand side, we have 3 nitrogens. On the right, you have 2. So something's wrong. So with this, one of the ideas, the quick little pro tips is let's even the odds, meaning you have 3 nitrogens on the left. So how can you even them out? Well, let's add a 2 here to make a total of 6, which is now even. So being that that is even, what we will now do is we'll put a 3 in front of the nitrogens over here, making 6 and 6 on the left and the right. Then we will now even out the nitrogens, making the problem balanced. So now let's actually get to the actual problem. So with this, assume you have 65.1 liters of nitrogen gas, and this is needed to inflate an airbag. How many grams of sodium nitride is needed at a pressure of 1.06 atmospheres and a temperature of 298 Kelvin? All right, now the first thing you always need to do is when you're looking at these problems is essentially find all the important pieces of information, right? We see that there's a volume here of nitrogen gas. We see that there's a pressure. We see that there's a temperature. And there's also an R value listed here. That's kind of letting you know, hey, this is a gas law problem. If you have pressure, temperature, that's a big red flag that should be going in your head that this is gas law. Another thing that can pop up is if you see the letters STP being presented, that's telling you also a context clue. Now it's asking you how many grams there are in sodium nitride. Well, you can't use the ideal gas law to get directly to grams, but you can get 2 moles of a gas, and then you can use the chemical formula to bridge that gap, right? So going from one step to another. So what we are going to do is we need to map out our moles and write down all the key pieces of information. So that way we can see exactly what it is that we had in the problem, right? So we had 65.1 liters of our gas that was presented to us. We have our pressure written down. So what can we start with? Well, if we have a volume, what we can use is the ideal gas law to get 2 moles. Now from there, being that we have a balanced chemical equation here at the bottom, we can use the mole to mole ratio, being that all this data here is representative of how many moles of sodium you have, right? So that is this purple area here. And what we are going to do is we're going to use that to convert to moles of sodium nitride, because it's asking, okay, how much did you start with in this problem to solve for that? So going from purple to red. Now that's using our chemical equation. Now we'll use molar mass to finish the job. So let's work that out. Let's do it. So the first thing we need to do is we're going to use our gas law to solve for moles. So why don't we do that for ourselves? So if we are to kind of look at this problem up here, so using our gas laws to kind of solve this, let's move our R value up. So the first thing we need to do is we need to plug everything in and rearrange our PV is equal to nRT equation. So if we are to do that, we need to get moles by itself. So what we will do is we will take our PV, which is on the left-hand side, and then we'll divide that by RT, and then make that equal to N. Because remember, it's originally PV is equal to nRT. So we're just moving pieces around. Now we're going to plug everything in. So we'll have 1.06 times 65.1. So 1.06 times 65.1. Then we're going to divide that by 298 times our R constant, which was 6.08206, times our temperature, which is 298 Kelvin. All right, now I know I didn't write all of our units in here, but we know in the end it's going to be making moles. So when we put this in our calculator, we'll have 1.06 times 65.1 divided by 0.0826 times 298. And you want to probably put these in parentheses so that way you solve it correctly. We'll have 2.82 moles of N2 as our answer. And now what we are going to do is we want to now look at our mole map to help guide us, right? writing these out can be really helpful because these problems are very long and it's easy to kind of get mixed up along the way. So our next step was using our mole to mole ratio using our chemical equation. So we started with nitrogen gas. So we have 2.82 moles of nitrogen and we need to go to NaN3. So we have 2.82 moles of N2 and we're going to convert that all the way to moles and then to grams in the very end. So we have 3 moles of N2 is equivalent to 2 moles of NaN3. And now in order to get this to mass, we got to use the molar mass. So 1 mole of NaN3. Then we'll take sodium, add that to essentially to 3 nitrogens. So by adding those two components together. So once we do that, we'll have 65.011 grams of NaN3. And what we're going to do is we're going to take 2.82 times 2 times 65.011 and then divide that by 3. And what we are going to get for our final answer is approximately 122 grams of NaN3 is what is required to inflate this airbag. Okay, so as you can see, we linked together gas law stoichiometry with mass stoichiometry together, right? It's bringing it all into one. So when we were kind of going through these paths, so if we take a look at our original molar map, we can see that we started up here where the gases were given, and we essentially went down using our ideal gas law, 2 moles, went across, and then went all the way straight. So this is the path that we took to get to grams desired in this problem. So notice that we didn't quite keep going up to gases. We went straight rather than making a left-hand turn. Let's take a look at our next problem. How many milliliters of 0.280 molar barium nitrate is required to precipitate as barium sulfate from the reaction with 25 milliliters of 0.350 molar aluminum sulfate? Now, with a lot of these problems, sometimes you're just given the names of different reactants, and you have to be able to convert them to their different chemical equations. So the first one is barium nitrate. If you remember, barium is a 2 plus charge, nitrate is NO3 minus, so you got to swap drop them, and we'll get BaNO3 2. Same thing with aluminum sulfate. We got to do the same exact practice. Now, predicting these, most solutions, being that we're dealing with molarity, typically are double replacement reactions. So we can see here is that we have AB plus CD. So we're going to be doing inside out, meaning the inside is going to bond together. So we'll have aluminum, and we just bring aluminum ion, so aluminum 3 plus, and that's going to be bonding with NO3 minus. We're going to trade the charges, right? Swap drop. So we'll bring the 3 outside of nitrate, just like so. So because we need to balance those two charges. Okay, so we have AlNO3, 3. Now the other species that we'll have is barium sulfate. So Ba is a 2 plus charge. Sulfate is a 2 minus charge. So they get reduced. We do not have to swap drop. All right, but is this problem done? And sadly, we got a balance, right? So really the easiest way to do this is use the polyatomics to balance. So let's say if I use the nitrates first, so if you look at the right-hand side of this problem, we have 3 nitrates here, and then we have 2 nitrates on the left. Let's even the odds, meaning being that we have 3 on the right, let's make that even. So how can we do that? Let's multiply it by 2, making a total of 6 nitrates, and then we'll multiply the left by 3, making 6 nitrates. So what I'm going to now do is I'm going to look at aluminum. So I'm zigzagging to aluminum. We have 2 of them. On the left-hand side, you see that you also have 2. So that's good. Now, what about barium? Well, if I do the same thing with the nitrogens on the other side, I see I have 3 nitrates over here. So what do I need to do over here? On the right-hand side is put 3 in front of the bariums on that side. Now, if you look at the sulfates, we see that we have 3 on the right and also 3 on the left. Everything is balanced. Now what we can do is we can kind of clean up our work, and this will be a balanced chemical equation, just like so. All right, so we're going to use this to be able to do our different chemical equations. First thing we need to do is map out the problem. So right here, I have the balanced chemical equation that we just put together. And then I wrote down all the key parts of information from the formulas or from the actual word problem. The most important thing is making sure you list the values under the chemical that they're talking about because it helps keep your brain a little organized. Now, when we're kind of looking at this, it's always really hard to figure out where exactly do you start because you have multiple terms that can theoretically get you to moles, right? If you remember, molarity or big M is equal to moles over liters. But the most important thing in order to get that to moles is you need to be able to essentially cancel out the liter component, meaning you need a volume. So the only one that does have a volume and a concentration is aluminum sulfate. So this is like where the green light is going to be of where exactly we can start this problem, is that we can start where aluminum sulfate is. So what we will first do is we're going to convert that volume to moles using the molarity. And then from there, being that it's asking us what the volume is of barium nitrate, so what is needed to do this problem, we'll use the mole to mole ratio and then essentially times or divide that by the molarity to get volume. So let's take a look. Let's do it. So the first thing, right, is that we were given 25 liters of our aluminum sulfate. So we have 25 milliliters of Al2 SO4 3, and we need to convert that to liters, which is always the very first step, is it needs to be in the correct units. So if we can kind of remember real quick, is that 1,000 mLs is equivalent to 1 liter, right? And from there, we are going to be using the molarity to convert liters to moles because mole is 0.350 molar is equal to 0.350 moles over 1 liter, right? These are equivalent to each other. And that's one of the hardest things to kind of remember is that those are equivalent. So with that being said, is what we are going to do is we are going to take that and do 1 liter is 0.350 moles. And that will get us to moles of aluminum sulfate. Okay, so Al2SO4 3. Now what we're going to now do is we're going to cancel all of our units. So we see mLs cancels mLs, liters cancels liters, and everything is nice and canceled the way it should be. Now, what is our mole to mole ratio? Well, this is where we use our chemical equation to get to barium nitrate. So what we can see is here is that there's 1 mole of aluminum sulfate, and that's going to be equivalent to 3 moles of barium nitrate. So it's a 1-to-3 ratio. So let's write that. So we'll have 1 on the bottom, so 1 mole of aluminum sulfate, and that's equivalent to 3 moles of barium nitrate. All right, so that will give us 2 moles. Now, what we're going to do for that last step is, so I'm going to make this a little smaller because I'm kind of running out of room here. So let's kind of just shift this over just a hair. And our last part, what we will do is, in order to cancel our units, is we are going to multiply or divide this by the molarity of barium nitrate, because that was given to us. So we can see moles cancels moles. And then we will divide that by the molarity, which, if we remember, was 0.280 for our molarity from earlier. Okay, so let's fill that in. So 0.280 moles is equivalent to 1 liter. And then we could see this cancels out. And then we're left with volume of barium nitrate. So what are we going to do here in terms of the math so we can read this? So let's kind of clear out some of the highlighting because it's kind of taking away the visibility of all these different components. So we are going to take 25 milliliters, times that by 0.350, times by 3, and then divide that by 1,000, then it equals, divide that by 0.280. Once that happens, what you should get as an answer is about 0.09375 liters of barium nitrate. And being that the problem asks for this to be in milliliters, we'll divide this number by 1,000, or sorry, times this number by 1,000, and we'll get about 93.75 milliliters as our final answer. Okay. And then being that this problem, we can try and check for sig figs as well. And I believe so that should be 3 sig figs in the end. So you'd want to round it to 93.8 as your very, very final answer if you were putting this into the correct sig figs. Okay. So that'd be for 3 sig figs. So that's how you would solve a solution stoichiometry problem. So let's go to the mole map and see exactly what route we took. So with this particular problem, we were doing a solution type of titration or neutralization problem where you're mixing solutions together. So with this one, where we started is that we had essentially about how much solution that we started with in the beginning. So we were down here where the solution was given. We then went up 2 moles. Then we went across and back down through solutions. So we stuck on the lower side. This was just using regular solution stoichiometry, which in my opinion is still the harder form of stoichiometry to follow. So we used molarity as a conversion factor to get the volume desired. Let's look at another problem. 60 milliliters of 0.322 molar potassium iodide is combined with 20 milliliters of 0.530 molar lead 2 nitrate. How many grams of lead 2 iodide precipitate? So with this one, we have our reaction. So I wrote out the reactants. So potassium iodide and lead 2 nitrate are reacting. So once again, double replacement reaction. So inside out. So we're going to have the inside react. So being that's lead 2, so it's Pb, and we'll have a little 2 plus. Now we'll have iodine, which is I minus. So being that we're going to drop those charges, we're going to have I2, and then Pb is going to stay with the same subscript. So we'll clean that up. Now we're going to have on the other side is we're going to have the outside react together. So we have K, which is a plus charge, and then nitrate, which is a negative charge. So we just have KNO3. Now, is it balanced? Well, we want to first look at the polyatomics. If you look on the left-hand side, you're going to see that there are 2 nitrates over here. And on the right-hand side, there's only a single nitrate that is there. So what are we going to do to fix that? Well, we will add a coefficient of 2 in front of the KNO3. Now we have 2 of those. So we'll zigzag, right, where we see that we need to balance out the nitrates, or sorry, the potassiums. We have 2 on the right. We only have 1 on the left. So we'll quickly fix that as well. And now we have a complete and balanced problem. All right, the next thing that we're going to do is write out all the pieces of information that we have. We were given our volume, which was 60 milliliters of Ki and a molarity of 0.322 molar. Then we have lead nitrate, which was 20 milliliters with 0.530 molar. And we want to know is how many grams of lead iodide are going to be made. Now, one thing you might notice is when it comes to solution stoichiometry, you need to do both the volume and the molarity to get the moles. So where do you start? And you'll see that you have all 4 of those values here. You have both the volume and the molarity for both. So what does that mean? You have a limiting reagent problem on your hands when you have both volume and molarity. So we need to solve for both of these getting to lead iodide. So let's first do it for the first one, which is Ki. So we have 60 milliliters of Ki. And what we are going to do with that is we are going to convert that to all the way to our moles of lead iodide. So we got to go from milliliters to moles. So first things first is we need to get this to liters because we need to be able to use our molarity, which is moles over liters. So just like we did in the last problem, milliliters cancels milliliters. Now what we are going to have is we have our molarity, which is 1 liter is equivalent to 0.322 moles of Ki. Okay. So when we look at this, we can see, all right, what's canceling out here? Liters of Ki cancels. And now we have moles of Ki. Now the next step is going to be all about trying to make sure that we get to moles of lead iodide. So this is where we got to use our chemical equation. And we remember that 2 moles of Ki, so I'm using teal blue to match the equation, is equivalent to only 1 mole of lead iodide. Okay. So these are equivalent to each other. Now, what that's going to do is when we solve this, we can see all of our units cancel out correctly. And this is going to give us moles of lead iodide. So when I calculate this, what we will get is 0.00966 moles of PbI2. Now, are we done the problem? Did I solve it and we're done? The thing is, we got to see how much does each reactant make? Which one runs out first? So we're going to repeat the same process, but with lead nitrate this time. So now we can see that our milliliters are going to be canceling each other out, which is great. Now we are going to convert this to moles using our molarity for lead nitrate. So what that is going to be is 1 liter of lead nitrate is equivalent to 0.530 moles of PbNO3. All right. So being that we have that, we will now use our chemical equation again to say that, hey, 1 mole of PbNO3 is equivalent to 1 mole of lead iodide. And when we solve this, so we'll take 20 times 0.530, divide that by 1,000, we will get 0.0106 moles of lead iodide. And now what we're going to be doing is we're going to compare essentially the 2 mole values we got. So the one that's in green here versus the one that's in purple, and which one is smaller out of the 2. And you can see that the top one, when Ki was fully used, made less. So this is your limiting reagent in this problem. So we're going to use this to calculate how much mass we had. So being that we only made about 0.0966 moles of lead iodide, the way that we would convert this is we would use the molar mass of lead iodide to do the final conversion. So pretty much what we are going to do here is we would look up our molar mass, calculate it, and what we would have is a pretty big molar mass for such a tiny molecule. So lead iodide is equivalent to about 461 grams of PbI2. So when we multiply those two values, you would get about 4.45 grams of PbI2 that is going to be theoretically created in this problem. So let's say if we wanted to take this one more step, which as you can probably have guessed, being I said the word theoretical. So all stoichiometry calculations are considered to be theoretical. So if everything goes perfectly, this is how much you should make. However, we are flawed. We make errors in labs, and sometimes you leave things behind. So let's say you only collect 4 grams in lab. What is your percent yield? So if we were to do this, you essentially just got to take whatever number you obtain, divide it by what you theoretically calculate. So 4.44 grams divided by 4.45, times that by 100%. And what we would have for our theoretical yield is 89.9% as our yield, which would be a very, very good yield. That shows that you were very careful when you were doing your measurements and your reaction went to completion. So let's take a look at our mole map to see what path we took. So with this particular one, we did have a limiting reagent problem, but they both started at the same point. You can have limiting reagents where you start at 2 different spots and you try to get to the same end goal. You still want to convert to the moles desired. You would follow the same process. So with this one, though, we didn't have to do that, though, which is kind of nice. We started at the solution level. So we started down here. And what we did is we converted to moles desired. We figured out what was our limiting reagent right at the moles desired. And then once we did that, we went to the grams desired. So both of these compounds kind of went together. So let's say we had like blue and red. And being that red made a little less, that one continued to the final step. It's all about kind of the perspective. You do them both together, and then you want to see like, okay, which one goes to the final finish line in this example, okay? So we use the molarity to convert volume, and then we use the chemical equation to get to the moles, and then we use molar mass to get to the final step. Let's take a look at another example. Our last example, 0.625 molar HCl is used in an attempt to neutralize 27.2 grams of sodium hydroxide. What volume is required to do this? So if we had sodium hydroxide and it was sitting in a beaker and we wanted to neutralize it, well, we could add HCl to do that. It would release a ton of heat and it would actually be a pretty intense reaction to do so. But where exactly do you start? Well, being that the first thing you need to do is we got to write out our chemical equation and then balance it. So we have HCl, and this is going to be adding to sodium hydroxide, so NaOH. So this is a double replacement reaction. So we're going to be having the inside bond to the outside. So sodium and chlorine bond together to make salt, so NaNCl. And then we'll have HOH making water. Now with this one, it's balanced the way it is, which is fantastic. So what we're going to do is list out everything we were given. So we have 0.625 molar HCl, and we want to know what is the volume in this case. And then we were given the mass of sodium hydroxide. So where can you start? Well, notice the one thing, so there's two things to notice. One is that you are giving a term that's by itself, and then one that is a conversion term. Now, when I say conversion term, remember that means fraction. So molarity is moles over liters. So you can flip it. It's usually never wise to start with the conversion term unless it's your only choice. With the mass, it's by itself. So you can start there. Now, the other thing to say is that with molarity, you need both the volume and the molarity to start with that value. We don't have the volume. You cannot start with that. So we're going to start with molar mass and convert mass to moles using molar mass. So we have 27.2 grams of NaOH. We are going to divide it by the molar mass to convert to moles. So let's do that. So we got to look up what our molar mass is of sodium hydroxide. So if you quickly do that, what you will quickly get is about 39.997 grams of NaOH for every 1 mole. So you just take 1 sodium, add it to 1 oxygen, then add it to a hydrogen. Now we'll cancel our units. So grams of sodium hydroxide cancels grams of sodium hydroxide. Now we'll use our chemical equation to get to moles of HCl. So we have 1 mole of NaOH is equivalent to 1 mole of HCl, which is great. But we need to now use the molarity to convert the last little bit. So let's kind of make this a little smaller for ourselves. And we'll extend this out. So this is where we're going to use that molarity term, which is 0.625 moles is equivalent to 1 liter. So we want to check that everything actually cancels. So moles of NaOH cancels, and then moles of HCl cancels moles of HCl. All right, so this gives us the volume, which is exactly what we are looking for in the problem, right? Is liters of HCl. So when we do this math, we'll take 27.2, divide it by 39.997, it equals, then divide that by 0.625. And what we are going to get in the end is about 1.09 liters of HCl is required to neutralize this. That is a lot. That's a lot of acid to neutralize this base. So you would have to measure out over a liter. Now, let's do a follow-up problem to kind of show all the different types of problems you can have, which is if the delta H of the reaction is negative 55.8 kilojoules, how much heat is released? So you have 2 options of where to start with here. The goal is when you have delta H of the reaction, this is equivalent to the coefficients in the reaction. So meaning that negative 55.8 kilojoules is equivalent to 1 mole of HCl or 1 mole of sodium hydroxide. So should you start with the liters of HCl or the grams of sodium hydroxide? I always recommend starting with the initial information given in the problem originally, not what you calculated. Being that most different homework assignments are auto-graded, it's generally always going off of what is initially given to you in the problem. Sometimes you might have to derive and go further and further and further in a lab. So then you could use the leaders here. But it's usually safer to start with the number you started with. So we will start it with 27.2 grams. And from there, you can pretty much follow almost the exact same steps. So what we can essentially do is just copy what we kind of have here on the bottom. So where we have 27.2 grams of sodium hydroxide, use that molar mass. And the only thing that where it's going to be different is that 1 mole of sodium hydroxide is going to be equivalent to negative 55.8 kilojoules. And that's for every 1 mole because of the balanced chemical reaction. If you had a coefficient of like 2 or 3 or 4, that number would follow suit. Okay, so if we were to do this, you'd take 27.2 times that by negative 55.8. And let me just move this over because I'm realizing it's getting cut off. And you would divide that by 39.997, and we would get about negative 44.6 kilojoules of energy is released. And negative means what type of reaction this is. This would be an exothermic reaction. So that to let you know. All right. So if you had a label, exo or endo. So let's go to our molar map to see where did we go. So with this particular reaction, we were given the grams of sodium hydroxide, which we then converted to moles of HCl. And from there, we went and used the molarity to get to how much solution was desired in this problem. So it went straight across and then went down for this particular reaction. So another type of problem. And as you can kind of see, that heat is not shown on this diagram. And that's because enthalpy probably is one of the more, I would say, not as common type of calculations that you do. Usually you do it a lot in thermochemistry or thermodynamics. And typically after that, you don't see it as much. That doesn't mean it's less important, but it's usually values that are given to you in tables and things like that, and calculating like bonds formed and broken if you have to take Gen Chem 1 or 2. So for stoichiometry, usually we always have to do a lot of solutions and a lot of masses, which is a little bit more important. So this has been the whole idea of trying to practice these types of reactions. I hope that this video helped. It was a little bit of a longer one, but practice problem videos always are. If you need help or weren't quite able to follow, please reach out, let me know, or put a comment below and let me know what you thought. And if you have any types of questions, I'd be happy to answer them. All right, thank you so much for watching and thank you for supporting the channel. Please like and subscribe if you haven't yet. And I hope to see you again for a future video. All right, I'll see you all later. Bye now.